Question number 11 says the solution to the differential equation y equals cos x passes through the point 0, 5 and use the tangent line to approximate the coordinate at y equals point x equals 0.1. So we're going to find the tangent line for approximation. So first thing is find the tangent line. To find the tangent line, we need a point, which we have here, and we need a slope, which we're going to get from this expression here. So the slope dy by dx at the point 0, 5, we just plug in x is 0, y is 5, so y times cosine of x, which is 0. Cosine 0 is equal to 1. So the slope value at that point is going to be 5. So this represents my slope. So then once I have my slope, I have my tangent line equation, which I'll call y, or we could call L of x, either or. I'm just going to say y equals L of x. And that's going to be my slope, and then my point. So x minus 0 plus 5. Okay, so there's my tangent line, and I'm going to then use this tangent line to approximate a point at 0.1. Okay, so I'm going to plug in x as 0.1. So my linear approximation at 0.1, I'm just going to plug that into my equation. I get 5 times 0.1 plus 5, so that gives me a value of 5.5. So that is my linear approximation of the solution y at x equals 0.1. Okay, so that is my tangent line approximation. The second part of this asks, is this an overestimate or underestimate, and how can we determine this using the second derivative? Well, if we take a look at here, if my second derivative is negative, I have a concave down situation. And what that means then is I have my tangent line is above the curve, which means it must be an overestimate. Okay, if my concavity is positive, or my second derivative is positive, my tangent line is now below the curve, so that's going to be an underestimate of any point. So that point, if you kind of imagine where that point is that point might be on the curve, and the point that we're estimating is on the tangent line. Well, that tangent line then represents an underestimate of that coordinate. So what we need then is we need the concavity of this. So what we're going to do is we're going to differentiate that expression again. So we say dy d squared y over dx squared is the second derivative of that expression. Well, we're going to need to use product rule. So we're going to do y prime times cosine x plus y times the derivative of cosine is going to be negative sine x. And so what we want to do then is evaluate this expression at the point 0, 5. Well, we can substitute in the expression for y prime as our original y prime expression here. However, what we can also do is we can just use the derivative evaluated at 0, 5 to replace that y prime here. And that's what we're going to do. So d squared y over dx squared is equal to, well, y prime, we calculated it up here as equal to 5. That's our slope at 0, 5. And maybe I'll just write it like this. So we're going to evaluate this at x is 0, y is 5. And that y prime value, we've already worked it out to be 5. And then we have times cosine of x, which is 0, plus y is 5, and times the negative sine of 0. Well, sine 0 is 0. So that's all going to be 0 on this. This is going to end up being all equal to 0. Cosine of 0 is 1, so we end up with a concavity of plus 5, positive 5. So our concavity is positive. That means then that our tangent line is an underestimate. So this represents an underestimate. Okay, because the second derivative, y double prime, is equal to positive.